that.
Okay, good. All right, so we have Q-tips.
So you're pretty familiar with the electromagnetic spectrum?
Well, what I want to, real quick, I just want to get your information recorded so that later on, if I need, oh God, his name, 20 years from now.
Oh, okay.
Yeah.
I'm Eric Brunner, 33 years old.
Okay. All right, Eric, you're what level of education do you have?
PhD in physics, but don't ask me anything about black holes or any of that.
PhD in physics. Wow.
Background's really in chemistry, biology, materials.
Okay.
Materials for biological applications.
Okay, so I'm really getting some nice exposure here at Dallas Makerspace. By the way, we're at Dallas Makerspace in Carrollton, Texas, 2017, January. All right, so I got the course on spectroscopy. Took physics of the atom. I had Dr. Brian in Texas A&M. I've seen some of this stuff, but I was a sophomore engineering student, and most of it went like this. I learned enough of the equations to get my B and escape, and that's just the way it went. So
That's how it goes.
yeah.
Are you familiar with the visible, the infrared, and the UV, ultraviolet?
Only because I worked in it subsequently in the industry. Otherwise, I would not have known that after college. Would not. But now, 300 to 700, 350 to 700, that's about what people see.
What you have to do with the net cal is you have to have it hooked in here when you first
So
turn it
like
on.
atomic spectroscopy, you have electronic transitions, and then you'll see peaks given off by that. So like, here's the Balmer series for the hydrogen atom, and we see these electronic transitions with the electron dropping down from the outer.
From
to lower.
you've got a valence shell thing going on. You've got this. It's the photon of energy that's released. It has the same h nu, or energy equals h nu, and it should be the same as the difference in quantized energy from one shell to the next.
Correct.
That's it, right? That's the premise, and that's how all this works. I forgot that. Thank you for reminding me.
So like that transition corresponds to that line, that transition to that line, this transition.
Well, those are wavelength in nanometers. Now, hold on. H nu. E equals H nu. H is Planck's is a constant, right? So nu. E is nu. Okay. All right, I get it.
Frequency, yeah, I'd have to be looking at those equations, but
Yeah. So fundamentally.
yeah. But yes, each one of these corresponds to a...
Oh no, there was a way to convert it to get lambda in nu.
Right.
Nu is.
the frequency.
And lambda is the wavelength, and so there's 1 over c, or there's a c in
That's
there
right.
somewhere. Yeah, remember. You need to understand, this is 20 years ago, right?
Yeah.
I'm still remembering it.
Hey, that's pretty good.
Yeah, I still remember it.
Yeah. So, just like we saw on the previous slide with the electronic transitions, molecules also have vibrational and rotational transitions between states.
Okay.
And so, like, here we have the vibration of a methanol molecule.
Make sure I can see the screen on this. It is 4K, so we'll catch most of it there. All right.
So we're seeing various vibrations for a methanol molecule.
Are those vibrations actually representative of really the way they wobble?
Yeah. And so, if you were to like put energy into this molecule, it would start wobbling in an excited state, and then when it lost that energy to light, it would transfer back to a less wobbly state.
Okay, so the red and black are protons and neutrons. The white are the electrons, right? Is that correct, or is it different atoms?
Different atoms. The
Okay.
white are the hydrogen.
Okay. So the size is representative of mass of the what do you call it?
The atomic amount?
Yeah, atomic mass.
Yes.
All right.
And so, with infrared spectroscopy, we're able to see these transitions between these modes of the molecules. So this peak here will correspond to some kind of transition, and that's the basics of spectroscopy.
The transition from losing that photon that is what is captured by those extra little spikes there, the added resolution. This is the resolution you were telling me about in the email that, people in the industry are going to want to be able to capture those extra.
Yes.
Okay.
So,
So it's not good enough just to have a spike that tells me what was present, what elements are present in the material, and in what quantities. That's not good enough. We need the
no.
JAGs as well.
Well, so you need the JAGs to get to the former. What I was saying with resolution, like if we zero in on this peak here, you see how it's got that kind of like pointed second peak there?
Mm-hmm.
So if you have a very, and this would have to be extremely, non-resolved or low-resolution spectrometer, you wouldn't be able to distinguish these peaks. It would just appear as one. You might see like a shoulder feature or something, but you're not sure it's there.
Sure.
So that's why you have to have high spectral resolution.